Okay, hello everyone. My name's Josh Bongard, and I'm part of the Proteus Institute, which I'm going to talk a little bit about today. You're watching Proteus TV. This is our streaming service associated with our institute, and on this stream you'll be able to find out all sorts of things about AI, robots, and biological machines. So before we get to that, just a few introductory remarks about who I am, what the Institute is, and what we hope to do. And then I'll dive into this very first stream on building some robots for you live on stream. And you can follow along and build your own robots using the Reddit link that you'll see at the bottom left of the screen. Hopefully audio and video is okay. So a little bit about the Proteus Institute. I'd like to talk first about the Institute's namesake, Proteus. Proteus was simultaneously a god and goddess. He and she was the Greek god or goddess of constant change. He and she was always changing form, always becoming something else. When we move from Greek myth into the natural world, we see that, of course, all plants and animals are constantly changing around us. You yourself look and act very differently than you did an hour ago, a month ago, a year ago, a few decades ago. If you look at our computers and our machines, they're not like that. They're pretty static. They keep the same form and do more or less the same thing until we tire of the machine or it breaks or we install some new software and so on. Most modern technologies are not very protean. They're not constantly changing, not constantly adapting, not constantly improving themselves like biological systems do. So together with some of my colleagues, we are trying to create what we're referring to as the Proteus Institute. And the Institute will try and create robots and technologies in general that also constantly change. So this stream is an opportunity for you to learn more about the Institute and hopefully get involved and work alongside us in trying to create protean machines and Proteus algorithms. And I'll talk a little bit more about those in a moment. But first, I just wanted to talk a little bit about the stream itself. As I mentioned, this is Proteus TV. At the moment, we stream live 1 hour a week. This is the very first stream. For now, we'll be streaming from 3 to 4 p.m. Every Friday, Eastern Standard Time. So hopefully you can join us. These streams are also being recorded. So if you click on the video link, which I believe is below you, you can see this and all the other videos we've recorded so far. You'll notice just bottom center, there's a logo there for NSF. NSF stands for the National Science Foundation. The NSF is one of the largest funding bodies here in the United States that supports basic science and research. NSF has invested in the Proteus Institute already. Part of that funding is to set up Proteus TV. So I'd like to take a moment to thank the National Science Foundation for investing in the first steps in creating the Proteus Institute. As I mentioned, it's not just me and the Institute. I'm Josh Bongard. I'm a computer science professor here at the University of Vermont. And at the moment, there are 3 other faculty involved in this project. Michael Levin, who runs the Levin Lab at Tufts University. Melanie Moses at University of New Mexico will be primarily responsible for the robotics side of the Institute. Mike Levin, who I just mentioned, will be involved and will be responsible for all of the biology aspects of the Institute. And finally, the 4th team member is Nick Cheney. Nick is here also at the University of Vermont in the computer science department, and he will be responsible for and helping out with all of the machine learning aspects of our Institute. So you can see we have a little logo in the top right, and I will show it to you a little bit larger here. I'll start out by pointing out our website. Hopefully you can see it here. It is proteusinstitute.github.io. We have a little bit of information there about the Institute as it currently stands. You can go and have a look, learn a little bit more about what we have in mind. I mentioned our team members. We have some workshops, a little bit more about our inspiration, Proteus, the Greek god and goddess, how to contact us, and so on. Here's our logo as it currently stands. At the center is the institute itself. We are hoping this becomes a national research institute, which is responsible for generating a broadening and ever outflowing flow of technology. And that technology is going to be broken into 3 different pieces: protean systems, protean machines, and protean algorithms. Protean systems are our word for all things biology. As I already mentioned, and as you know, every living system on the planet is constantly changing. It is a protean system. It programs itself, it adapts, it improves, ourselves included. We will draw on what we know and try and learn about what we don't know about how biological systems change and adapt, and funnel those discoveries and observations into the Institute, where an AI will try and learn from biology and take what it's learned to turn around and generate protean machines. So we are creating an AI that can design various forms of physical machines. These are meant to be protean machines. They're meant to be able to also constantly change their bodies and brains to adapt, recover from surprise, and become better at what we would like them to do. We'll probably be looking a lot at soft robots. So these are robots that can deform and change their shape, or be deformed and have their shape changed. We will also focus quite a bit on computer-designed organisms, more popularly known as xenobots. Together with Mike Levin and myself, our group generated the first wave of these computer-designed organisms, which are built not from plastics and metals and ceramics and electronics, but they are built from cells. This particular computer-designed organism, or xenobot that you're looking at here, is made from frog cells. Nick Cheney is going to be responsible for a lot of the machine learning aspect of the project. We'll help the AI at the heart of the Proteus Institute to, again, learn from biology, learn from what it makes, from the robots that it makes, and use that knowledge to make new kinds of machine learning algorithms that are more protean than the ones we currently have. Algorithms are better able to change themselves than robots are, for the very reason that they're not physical. But even our most state-of-the-art AI and machine learning methods are not very good at reprogramming themselves. We hope that the AI lying at the heart of the Proteus Institute learns how to create more self-adaptive AI methods. So that's the goal for the Proteus Institute. That's what we hope to do. So there's going to be a lot of biology, a lot of robotics, and a lot of machine learning in our institute. And today, because of the stream, I want to stop talking at you and focus today in particular on robots. And I'm going to actually code up some robots live on stream. We'll see how that goes today. What I'm going to try and do is to create the virtual robot that you see, the simulated robot that you see bouncing around above me there. And you'll be able to follow along if you know how to write in Python by directing your browser to the Reddit link you see at the bottom left, which is www.reddit.com/r/udobots. Okay. I'm going to focus on robots today because that's my area of expertise. I am not going to be the only presenter on Proteus TV. As I mentioned, there'll be an episode every Friday at 3 p.m. There'll be some other members who will be interviewing scientists, doing other code-alongs, diving into the philosophy and the psychology and the engineering and the biology and the physics of what we have in mind. So you're going to see a large diversity of faces and ideas on this stream, and we'd love you to join us for those future episodes. Again, I realize I'm talking a lot. I'm going to stop talking in a moment and start doing. Because this is a Twitch stream, please do feel free to type any questions in chat at any time. You're never interrupting. We'd love to hear from you. I'm happy to answer any questions you have, whether they're relevant to what I'm doing at the current moment or not. So again, thanks for joining us. And without further ado, I am going to switch and start coding up some bots for you. The Ludobots link that you see bottom left, this is a robotics MOOC, or massively open online course that I created a few years ago. I use that with my students here at the University of Vermont to teach them how to code up robots in simulation like you see above. So I'm going to start this course from the beginning. I'm going to put on my student hat and pretend to be a student in the Ludobots course. You can watch me code along. Better still, direct your browser to reddit.com/r/Ludobots. And when you arrive at this subreddit, you'll see that there's a post at the top that says Start Here. If you click on that link, it'll take you to the very first link in the MOOC, which is installation. So in order to start coding up some robots, we have to start by, hopefully you can see that. You have to start by installing a little bit of software. You're going to be installing PyBullet, which stands for the Python-based Bullet physics engine. So Bullet itself is a particular kind of physics engine. You're seeing a Bullet virtual world above me there. And what we're going to be doing today, and what you're going to be doing if you follow along, is to create or generate a robot inside the Bullet physics engine. Okay, so this particular stream is going to be a little bit like a cooking show. I'm going to skip over some of the boring parts. I have already installed PyBullet, so I'm ready to move on from the installation step. I'm going to move on to the next learning module in the course, which is simulation. Okay, so we're going to start creating an empty simulation or an empty virtual world, which will look like the one above me, but it'll be missing the blue robot and the white box. Okay, so a little bit of preliminary information here. Again, in the interest of time and the interest of interest, I'm going to skip over these preliminaries. Please do not skip over these if you're taking this course. It'll allow you to keep your code clean and organized on GitHub. I'm not going to talk about what GitHub is. We're going to skip over that today. And I'm going to start by creating an empty file called simulate.py. The .py is a, oh, let me just open a coding window here to begin with. I'm going to create a empty file called simulate.py, which is where we're going to do all of our work. Give me a moment to get set up here. There we go. Okay. Okay, so I'm going to create a new file called simulate.py. I'm old. You can see I have a little bit of gray hair. So I work in one of the oldest and the best text editor and code editor on the planet, Vim, known as VI for short. For the youngsters on the stream, this may look a little surprising, so please bear with me. So I'm going to open this empty file in Vim. There's nothing in here at the moment. I'm going to add just a single line, which is just pass. So pass says, as the name implies, if we run this code, it's going to do nothing. Okay. I'm now going to run this piece of code. There's nothing in there, so obviously it's not going to do anything. Okay, so we sort of have a blank palette that we can begin painting our simulated robot onto. Okay, so we've created this file called simulate.py. First thing we're going to do is to import into this file the PyBullet physics engine. So to save myself some time, I'm just going to copy and paste. Okay, so now we're at least importing this physics engine. If I run simulate.py now, okay. I get a little message back from PyBullet, so that's just a little ping to let me know that it's actually, it's there. So all's good. For those that are just joining, my name's Josh Bongard. I'm a member of the Proteus Institute, and I'm coding up the simulated robot that you see above me today. Please follow along at the Ludobots subreddit. Okay. First thing we're going to do is create what's called a physics client. So this is just a data structure that is going to sit inside of my code, and I can then use that physics client to create my physics engine. So I'm just going to copy this piece of code. It looks a little cryptic at the moment. I'll explain a little bit about what you're looking at here. Just remember that for now, P is short for PyBullet. So everywhere you see a P dot in the code, whatever comes after the dot, these are commands or functions that exist inside the PyBullet simulation development kit. Okay. So once I've connected to the physics client, I'm immediately going to disconnect from it. Okay, so import, connect, disconnect. So still not very interesting. Shouldn't really do anything except just not crash. Okay. You'll notice there's a little bit of a difference. You'll notice whenever I run this, there's a short burst in which a little window opens up and then immediately closes. So that window is going to be our window into the PyBullet virtual world. It also spits out a whole bunch of cryptic messages, which we aren't going to worry about for now. So I'm able to create and then immediately destroy this virtual world by connecting to the physics engine and then disconnecting from it again. Okay. What we're going to do now is when we create this world, we're not going to immediately destroy it. We're going to create a for loop that is going to step through particular instance in time in this physics engine. So if you think about a movie made up of a series of frames, if you pause at any one frame in this movie, that corresponds to a particular point in time in that movie. In the same way, if you think of a physics engine as a movie or something that is changing over time, we can step through that virtual world and pause and do things at particular points in time in the physics engine. So I'm going to start by creating a for loop. So after we've connected to the physics engine, okay. So my for loop variable is going to be called time step. The first time through this loop, and I'll just print out the time step inside the loop so that the loop is actually doing something. First time through this loop, time step is going to equal 0. Next time through this loop, time step is going to equal 1. Next time through the loop, 2, and so forth. So if I run this code now, we should see the numbers 1 through 1,000 printed out. It goes pretty quickly. I'll try to do that again for you. And again, and again. Okay, so we open the physics engine, we step time from 0 to 999. Or up to 1,000, and it goes very fast, so we don't even have time for anything to happen. So this is like running a movie at super fast forward. The movie runs past so quickly you don't even see what happens. Okay. Okay. So what we're going to do now is slow things down a little bit, and we're going to do so by using a second Python package called time. So I'll start by importing the time package. Inside time is a sleep function, which basically sleeps your computer program, or your Python code in this case, for a set period of time. And what it expects inside is we need to tell the sleep function how long to sleep for. We're going to sleep for 1/60th of a second. So the number inside here, which is 1 over 60, is just telling the time library that we'd like to sleep or pause on this particular line in the code for a 1/60th of a second. Okay. If I run simulate.py now, you should see the numbers at the top left are scrolling past slower, and you'll notice we get our first view into this physics engine. Not much is happening at the moment, but we have this physics engine, and we're flipping through the frames in that video, or we're stepping through time in that physics engine a little bit slower. So we have time to see what's going on. So while we have this time, while this is slowed down a little bit, let's think a little bit about what this physics engine is. This is not actually a movie. This is actually something that is live. And I should be able to interact with this virtual world. Let me try that again. I'm not having much luck at the moment. This is the Murphy's Law of live streaming, is that what you expect to happen doesn't exactly happen. Let me just have a look here. Did I miss something? Aha, yes, I missed something. Okay, so there's another line that has a P dot in front of it. This is a reminder that this is from the physics engine PyBullet. So if I go back into simulate.py, I need to include this line, step simulation. What this line is going to do is Python is going to head down into our code. Sorry, let me just pause for a moment. Things are running a little slow on my machine. Okay, so let's try that again. Okay, we're going to step the simulation, which means PyBullet is going to take over for a very short period of time at that particular point in the physics engine, and it is going to step or update the physics at that time. At the moment, there's no real physics going on because we aren't really doing much. So let's just see what happens here. Like before, we've got our virtual world. Time is running forward from 0 up to 1,000, and now, hopefully, you should be able to see that with my mouse, I am clicking on the world and rotating a camera, which is showing us that in real time we can interact with this virtual world. There's nothing in that virtual world at the moment, but there will be in a moment. We're going to be adding this virtual robot to our virtual world in a moment. Okay, so we've got our empty physics engine, so we're making good shape here, and we're in good shape here. So controlling the virtual camera, the only thing that exists in our virtual world at the moment is an actual virtual camera. And when I click on that window and move my mouse around, I'm moving where the camera is looking at the same time. Again, this is just a reminder that we're not playing back a pre-recorded video. This is something that's being simulated live whenever we run our code. Okay. How to submit your homework. No actual homework today. We're just playing around, so we'll skip over the boring bits as promised and move on to adding some things to our physics engine. What are we going to add to our physics engine? We're going to start to add links. What are links? These are going to be the 3D objects that make up our robot. So in the video you see above me, if you count carefully, you'll see that that blue robot is made up of 9 parts. There's the main body, and then 4 legs. Each of the 4 legs has 2 parts or 2 links. So you have a total of 9 links that makes up that blue robot. There's also a white box just off to its right. That's a 10th link. Why is it called a link? I don't want you to think about links as links that connect objects together. Instead, I want you to think about sausage links, so sort of the actual objects themselves. It's a little bit of confusing terminology, but this is drawn from PyBullet and other robot simulators, where they think of the things that make up the robot as links in a chain or something together that makes up the robot. Okay, so we're going to start by adding some links to our world, some physical objects. Okay, we're going to skip over again, taking care of our Git repository, and get to the good stuff. Okay, so the first thing we're going to do is we're going to include a third package called Pyrosim, and Pyrosim is a little bit of a wrapper around PyBullet. Remember that PyBullet is the virtual world. Pyrosim is some additional code that's going to make it easier for us to create virtual robots. And I'll talk a little bit more about what Pyrosim does when we start using it a little bit more. So the first thing is I'm just going to copy and paste this line. This is going to go into our code. We're going to include this in a new file that we're going to create called generate.py. So we're going to use Pyrosim to generate a description of our robot. That's the generate file. The simulate file is then going to read in what generate generated and simulate that or whatever generate generated. So let's start by creating an empty generate file. Like before, I'm just going to add an empty pass for now. It's not going to do anything. Generate doesn't do anything. We still have simulate, and simulate it doesn't simulate anything. It just creates an empty world. So generate's going to spit something out. Simulate's going to read it in and simulate it. Okay. We're going to use Pyrosim in generate.py. So we're going to include it. And I'm going to make a slight change here. This is, again, part of the boring stuff, not important for us. And when I run generate now, I'm going to get a little message back, a little pip, and this is just a reminder to me that it's included this library correctly. Okay, so let's generate something for simulate to simulate. Okay, so the first thing we're going to do is we're going to add this line, which again looks a little cryptic, but I'll describe what it's doing. And get rid of our empty pass statement and include this. So Pyrosim reminds us that this start SDF is a function that belongs to Pyrosim. SDF stands for Simulation Description Function. So there's a website for this. Simulation Description Format, sdformat.org. You can go and check this out on your own. This is a standard file format that's used in the robotics community. So we're going to start to see some .sdf files. If you open an .sdf file, it tells you how to simulate a particular robot. That's what the SDF file is for. Okay. So we're going to start an SDF file, and it's going to be called box.sdf. Once we start creating that file, we're going to end that file or close it. So let me just add an end here. And let's run generate.py now and see what happens. So I'm going to run generate. Doesn't look like it did anything. But if I have a look at all of the files in my directory, you'll see that there was a file that was just created just now. It is actually 3:26 p.m. Here in the US. Created this file called box.sdf. If I open this file, you'll see that it's just got a little bit of a few tags here in it. For those that are familiar with this, this formatting, you'll probably recognize what this is. I'm not going to talk too much about this for now. There's nothing in there, so we haven't really generated anything except an empty file. So now we're going to add this line, which is going to send a cube to the SDF file. Open the generate file. So I'm starting an SDF file with this name. That file is now open. I tell Pyrosim to send a cube into that file. That I'm going to actually get rid of everything inside here. It's a little confusing for now. So we're just going to send a cube for a moment. I'm not going to tell Pyrosim anything about that cube. Just send a cube and let Pyrosim figure out the rest. And then close this FDF file again. Okay. Before I run generate.py, let me remind you of what's in box.sdf. At the moment, not much. If I run generate.py now, and it seems like it's going to hang on me here, not too much is going to happen, except that my terminal is going to freeze on me. Okay, that did not work too well. Again, part of the joys of live coding. I think what happens is Pyrosim needs a little bit more information. I took away too much information and it got confused. So let's try this again. Let's tell it just the name of the object or the cube that it's creating. The name is box. Hopefully that's enough. Let's try that. See what happens. Okay. All right, it just needed a little bit of information. So now let's go ahead and open box.sdf. And you'll notice between the SDF and the /SDF down here, there is quite a bit of information. I can't read it. Even I think someone who's well-versed in SDF file formats can't read it either. It's pretty complicated. This is what Pyrosim is for. So you'll notice that 1, 2, 3 lines in Pyrosim allowed us to create a much more than 3, an actual 32 lines in box.sdf. So what Pyrosim is doing is sitting between us and the physics engine and it's greatly simplifying what we need to tell Pyrosim, and then Pyrosim is able to provide more details to the physics engine. So the physics engine is very complex, very intricate, so it's sort of acting as a middleman or a middle person between us and the physics engine. This is how you actually tell PyBullet, the physics engine, how to simulate a cube. This is how you tell, this is how you tell Pyrosim to send a cube. A lot simpler. Okay, so we've been talking a lot about cube, so let's generate that cube. It's now in that file box.stf, and we're now going to read whatever is in box.stf into simulate.py and simulate it. Okay, so how do we do that? We need to simulate this box, so we're going to tell simulate.py to load in this file that was just created. Okay, so now when we run simulate.py, hopefully, there it is. Okay, so now we see that we have generated a cube. It's been stored in a file called box.stf, and simulate.py read in that box.stf file and simulated everything in that box.stf file, which in the moment is just a single cube. Okay, not rocket science, pretty simple to start. Okay. You'll notice a couple things about when we simulate this cube. The first thing is that it's just sort of sitting there in space. If we look at the ground, you'll notice it's actually embedded in the ground, which we'll come back to. It's also not moving at all, so it doesn't look like there's much that's very complicated that's happening at the moment. You'll notice that there's not very much that's interesting that's happening at a moment. So let's see about this box for a moment by actually simulating this. Okay. If I run this again, if I grasp this object, you'll notice that I can actually manipulate it. So I'm now clicking on my mouse when my cursor is over the box, and we'll notice that I can manipulate this object. Okay, so we know that we actually have a simulated, we have a virtual simulation here, and we've created a simulated box inside that virtual world. Okay, I think my computer's running a little bit hot because I'm streaming and simulating and talking and coding all at the same time. Things look a little bit better now, so let me just try that again. Okay, so we have an empty simulation. Here's our box, and I can click on the object, and by scrolling, I can manipulate that object. So far, so good. Okay, so we now have a virtual world. We have a single link, a single object that's inside the world. You'll notice in the video above us that we now have the box that sits next to the robot. What's the next thing we're going to do is to actually start simulating this blue robot itself. Just a reminder, if you're joining the stream, I'm coding up some simulated robots. I'm Josh Bongard. I'm part of the Proteus Institute. Please feel free to stop me at any time and ask any questions about Pyrosim, robots, NSF, Proteus, who am I, who are you? No question is out of bounds. Okay, so let's move on to the next module in the course, which is after links is many links. So we're now going to create a robot that's made up of 9 links or 9 objects. Okay. Again, we're going to skip over some of the preliminaries here. We're going to move on now to starting to add some forces to our virtual world. We were just adding objects. We can also start to add additional physics to this virtual world. At the moment, the block itself didn't move until I started manipulating it because there was no gravity operating in this world. It was basically an object that was hanging in outer space where there's no gravity. And an object in space, unless something else interacts with it, will stay at rest and will only start moving if something hits it or if a force starts acting on it. So let's add a force to our simulated world. And we're going to do that in simulate.py. I'm going to add it right here. So right after we create a physics client, we're going to tell PyBullet something about this world, which is there's minus 9.8 meters per second of force acting on objects, pulling it downward, minus. Okay, so now when I run simulate.py, hopefully what we should see is not a stationary object hanging in space, but instead, fingers crossed, an object that slowly starts to fall forever downward. Okay, so now we have this force acting in any objects that we place in the world. Gravity is going to try and pull them down unless they exert some force of their own and try and do something else. Okay. You'll notice that the cube kind of fell, quote unquote, through the floor or under the floor. That's because, technically speaking, there is no floor yet. You'll notice in the video above me there's a checkered floor, but if I run simulate.py, you'll see there's just some pencil lines where a floor should be. That's just sort of telling us about the 3D coordinate system in this space. There isn't any actual floor, so let's add a floor. We're going to do that by adding a particular line that just tells PyBullet. Remember, the P dot tells us that we're working with PyBullet. And we're going to add this, then add this in here. Okay. You'll notice that now we're loading in not an SDF file, we're reading in a URDF file. This is the Unified Robot Description format. If you Google URDF, actually I can just go ahead and do this for you. If you Googled URDF, you'll come up with all sorts of crazy things, but if you Google URDF along with SDF, that should take you to the robotics pages that explain the difference between these two file formats. Not so important for our purposes today. Okay. We can skip over that part. Okay, we've read it in, and I think we should be able. Oh, right. We have to also tell PyBullet where this particular file is stored. So again, a little bit of boring stuff, but I have to do this. So I need to import a new file here. This is all explained in the MOOC or the online course. If you're interested in the nitty-gritty details, I'm not going to talk about this at the moment because I don't want to put you to sleep. Okay, so that should allow PyBullet to find this file, which comes with PyBullet. Remember that box.df did not come with PyBullet. This is a file we created. Okay, so if I run simulate.py now, we should see a floor. There it is. Okay. You'll notice that now the object does not fall through the floor and keep falling. It actually jumps up in the air and then slowly starts falling back down again and eventually hits the ground and stops moving. So we successfully have a floor. I don't know if we have any advanced users with us today, but does anybody know why the object now actually jumps up in the air and then slowly falls back down? If you have an idea, go ahead and type it into chat. I'll give you just a minute. If we don't have any advanced users or if everybody's shy, I'll wait and then carry on. Okay, while we're waiting, just watch this one more time again. There's our cube, jumps up in the air, and then slows down and will slowly start falling back down to Earth again. Why does it jump up in the air at the beginning of the simulation? So the reason why is if you watch at the very beginning, the object, the cube, is placed at coordinate x equals 0, y equals 0, z equals 0. So 0, 0, 0 is a coordinate in this world, and it's the center, literally the center of the universe here. that puts the cube inside the floor, and we have two links. We have two objects, the cube and the floor, that are interpenetrating one another. The physics engine knows that generally objects should not be touching or interpenetrating one another, so the physics engine will start to apply additional forces, other than gravity, to try and push these objects apart. As the cube falls down again and comes into contact with the ground, it will actually pass slightly below the ground, and now the cube and the floor are interpenetrating, and the physics engine will apply a little bit of force to push it back up again. Gravity will pull the cube back down. The physics engine will push the cube up because it's inside the floor, and those two forces, the gravity and resolving the collision, those two forces will eventually cancel out, and the cube will stop moving and rest nicely on the floor. Okay. So that's a little bit unrealistic, right? You don't typically have objects suddenly materializing inside other objects, at least not until we create the Star Trek transporter system. So let's fix our simulation a little bit. Let's fix our cube, which is the only thing that we're generating at the moment. So let's tell Pyrosim where to place this box. Okay, so the PyBullet virtual world here is 3 dimensions, so we need an X, Y, and Z coordinate. We need to tell it where to put it. So X, as you can imagine, is horizontal, and in the picture, in the video that you see above me, it's the robot is a little, or the camera is sort of diagonal. So left and right, or left and into the screen, and right and back towards me. It's a little confusing, but we're going to leave it at x equals 0, so horizontally on the ground. We're going to leave it at y equals 0, so not towards me and not into the screen, so 0, 0. And z in this case is going to be the height of the object. So I'm going to move the cube up 2 units. So what do I mean by 2 units? It's not clear here if units is meters or inches or centimeters, or we don't know what the units are here. PyBullet kind of ignores it and just says, doesn't matter if it's meters or inches or millimeters. We'll just assume units, 2 units. Okay, so let's see what that looks like. Remember that we made a change to the cube, so we need to run generate.py. And it didn't like the keyword position. That's my fault. Pyrosim likes us to be concise, and I'm just going to use pause. That should be right. Okay, no complaints. That was just compiled at, let's see, 1:23 p.m. Okay, I'm not sure what time zone PyBullet is in, but if I have a look here, there was a file that was just created called box.stf. So we know that when we just ran generate, when we just ran the file called generate, it generated this box, and if we now simulate this box, we see that it's placed 2 units above the ground and starts to fall. Okay, so far so good. So we can alter the position of the cube. Let's, instead of putting it at 2 units, let's put it 200 units above the ground and see what happens. Let's generate the cube and then simulate the cube. Doesn't look like we can see the cube, but if I now rotate myself under the ground and look way up from under the ground up into space, I still can't see it because it's so high up there. It's somewhere 200 units above us. I can actually see it. Can you see it? It's a little gray speck there, and it is very, very slowly falling back to Earth. Let's see if it makes it here before the simulation gets to 1,000 time steps. I don't think it's going to make it, so let's break out of here and let's try something else. Let's bring it a little bit closer to Earth. Let's bring it down to 20 units. Okay, we'll generate it to sit 20 units above us. Let's see if we can simulate that. Okay, there it is. It's falling towards us. Here it comes. Okay. I'm just going to try and run this in a little lower priority, see if that helps. The stream. I think simulating and streaming simultaneously doesn't work too well. Let's see if that's a little bit better. Okay. A little bit better, a little bit better. So let's bring it back down to Earth a little bit further. Let's bring it to 10 units above the ground. Let's generate that. Let's see if I can stream and simulate at the same time now. I'm going to nice this process, meaning it's going to run in lower priority and allow the stream to take priority. So hopefully things aren't as choppy. Let's try that. And there's the object above us, very slowly falling back to Earth. Here it comes. Okay, I think we're streaming and simulating a little bit better now. I apologize for the technical difficulties. This is our pilot episode, so you have to bear with us. Falling back to ground, and there we go. We have the cube coming back down to Earth after being placed 10 units above us. Okay, so hopefully that gives you a sense of how you can create a cube or create a link, an object in the physics world, and then alter where it sits in that world. We can also alter other properties of objects as well. So for example, I can specify the size of the cube. At the moment, Pyrosim assumes a default size. So let's set the size of this cube to 1 length unit in length, 1 length unit in width, and 1 length unit in height. So length, width, height. Okay, so we want a cube. We want to place it at this position in the virtual world, and we want it to have this length, this width, and this height. I'm going to generate that, generate, and now simulate this new box. And I'm going to put it back down a little bit so it doesn't fall from Earth. We can see it a little bit better. So let's put it at 2 units above the ground. Generate this new description of that cube, simulate it. There it is. We don't see any change because the default size of an object here is length 1, width 1, and height 1. Okay, so let's change some of the dimensions here. Let's change this dimension. Let's make the length half of the others. To generate the cube, simulate the cube. And we can see along the x-axis, hopefully you can see my cursor there, along the x-axis it's been narrowed a little bit. So we can alter the shape of our cube, or shape of our objects. It's not a cube, strictly speaking, if length, width, and height are not the same. Okay, so I'm going to put it back to 1, 1, 1, make sure I altered that change. Make sure that that change took hold, and then there's our 1 by 1 by 1 cube. Okay. Okay, so let's move on and do something a little bit more interesting than altering the position and shape of a cube. Okay. We just went through size, so we can skip over all of this. We just played around with changing the link position. That was fun. Let's make some more links to start with. So that's pretty easy to do. I can go back to generate, and I can just duplicate this line and call this box 2. Not very creative. You'll notice that box 2 obviously now has the exact same position and the exact same size as box 1. Let's call this now box 1. Again, not very exciting. What happens if we now simulate these two boxes that have the same size and the same position? Let's see what happens. you'll notice that those two objects are interpenetrating. So the physics engine, again, does not like objects that interpenetrate. So the physics engine applies forces to push them apart. So let's help our physics engine out. Let's call this lower box, and let's call this upper box. And as the names imply, we're going to try and put the upper box on top of the lower box. We'll keep the two boxes, or the two cubes, to have exactly the same size, but we're going to put the lower box down low at a height of 1, and we're going to put upper box at a height of 3. I'm also going to swap the order of these lines so it just reads a little bit easier. So we're going to create an upper box at height 3 and a lower box at height 1. Okay. I'm now going to generate that new description for our simulator. Simulate that. And there's our lower box and our upper box. Lower box hits the ground and the upper box comes into contact with the lower box, and we're all good. Okay. So far, so good. Okay, so at this point, we have about 9 minutes left. I could move on and start talking about how to connect objects together, like you see in the blue robot. We could start adding sensors and motors to our robot, but that's a little bit more involved. That's probably best for another day. So I think what I'll do instead is we'll go off on a little bit of a tangent for a few minutes and look at how we can play around with physics engines, and we'll talk more about robots inside physics engines next time. While we're just pausing and pivoting for a moment, just a reminder that if you have any questions about the Institute, about physics engines, robots, please feel free to ask me any questions. Going once, going twice. Okay, so let's move on to a slightly different concept, which is in robotics. Obviously, we usually don't want to just simulate. A robot in a very boring world with an infinite flat plane and just a couple of objects in their environment, because obviously the real world doesn't look like that. So one of the things that's interesting when you work with simulation is you can construct interesting or complex environments for your robot to navigate. So in the 8 minutes we have remaining, let's actually try and create a slightly more interesting environment for our robot than the two boxes you just saw. And I'm going to do that by doing by procedurally generating some content. So PGC, procedurally generated content. We're going to do that now. So procedurally generated content, I'll just write this down for you here. Or PGC, this is a concept from game development. As you can imagine, in most modern video games, when you look in those virtual worlds, they're incredibly complex. There isn't a game developer who went in and generated or described one blade of grass in the latest first-person shooter, and then the next blade of grass and the next blade of grass. Instead, the games programmer took one step back and wrote a procedure that generates content for the virtual world. We're going to do that now. So let's create a procedure, and that procedure is going to be simply a for loop for height in range 1 through 10. Okay, so we're going to step through different heights, and as you might already be able to imagine, we're going to put one box at height equals 1, another box at height equals 2, a third box at height equals 3, and so on. So I'm going to get rid of one of these lines, and I'm going to leave just one statement inside this loop. So this loop is going to loop 10 times and call this function 10 times. And every time it does, we could put place the object at the same position, and we'd have 10 cubes all on top of one another. But that's no good. We're going to try and stack them vertically. So the first thing we're going to do is have to give each of these boxes its own name. So cube name equals box. And we're going to add height as the name. So actually I'm going to just comment out this line for a moment, and let's print out the names of these 10 cubes. Make sure we've got the names right. Okay, there we go. Actually it's going to create 9 boxes. That's perfectly fine. Okay, so we have a name for our cube. Each cube has its own name. That's important. Okay. The position of each cube is going to be at x equals 0, y equals 0, and z, the height, is going to be equal to the height variable, right? Okay, so first time through this loop, height equals 1, second time through, height equals 2, and so on. Okay, so let's run this code. Let's generate these 9 boxes first, and then let's simulate them. Okay, let's see how this works. There are our 10 cubes. You should notice that we have a stack here. There's our stack reaching up into the sky. So we have a stack of 10 cubes. It just looks like a tower. How do we know this is actually working? Let's grab one and pull it out from underneath and see what happens. Okay. So you can see that we actually are simulating something here. I'm going to stop this simulator because I'm learning that streaming and simulating don't mix. So I'm just going to try and minimize the speed of these simulators. I'll give my computer a moment to recover after that heavy simulation. Let's actually try it. Let's try nicing this process again and see if that helps. Okay. Hopefully the stream is a little smoother now. We'll see. And we'll try this again. I'm going to grab the lowest of the 9 blocks and pull it out from underneath this tower, and we'll see how this changes the behavior of the simulator. Okay, I think that still slowed down the stream quite a bit. So although it looks okay now. So we built this tower by creating procedurally generated content, and along the way we altered the positions. We placed one block on top of it. Let's now make a Hanoi tower where every block that's placed on top is smaller than the block below it. Before I show you how to do that, I want you to have a look at this piece of code and see, for those of you that know how to code a little bit, can you think about what I need to alter to make every new block a little bit smaller than the one below it? We want to assume, or we're going to assume, that the lowest most block has length and width and height of 1. The one above that is going to be a little bit smaller and a little smaller and a little bit smaller. The easiest way to do this is to write the length here, and we're going to set this to 1. And we're going to replace this number with a variable. We're going to do the same thing here. And the same thing for width. Okay, so now we can alter these 3 variables as we see fit. We know that the first time through this pass, oh, actually we have an issue now. We have 2 variables called height and height. So let's do L and H and W. Okay, so the first time through this loop, height is 1. Second time through this loop, height is 2, and so on. So if we divide by height, I'm going to put a little dot to just, this is a little bit of Python stuff here. And same thing for height and width. Okay. So now we're going to divide 1 divided by 1. The first time through the pass is 1. Second time through the loop, when we're making the second cube, 1 divided by height equals 2. 1 divided by 2 is 1/2. So it's going to have a width of half, half, half. Next time through, the third cube is going to have a length, width, and height of a third, a third, a third, and so on. Let's see how this works. So we're now going to generate this new set of cubes. I put the dot in the wrong place. My apologies. Let's try that again. And let's simulate this one more time. Hopefully it doesn't disrupt the stream too much. And there you go. We've got a smaller object on top of smaller objects on top of smaller objects. Okay. Okay, clearly there's a few issues here to work out. I'm going to work on simultaneously streaming and simulating for you so this works a little bit better next time. Thanks very much for joining us. As I mentioned, this is the first of several streams on Proteus TV. This is part of our public-facing aspect of the Proteus Institute. We hope you'll join us on Fridays at 3 p.m. We'll have some other guests next time that will be presenting some other aspects of robotics, biology, and AI. I will be back on a future stream to continue this process and show you how to create virtual robots. Thanks very much for tuning in, everyone. Have a good rest of your day.